MCV4U lesson on asymptotes and sketches. So this is a continuation of a couple of things. A continuation of what we started this unit in sketching graphs, and also what we started in MHF4U when we were graphing rational functions. And we're going to add a little more detail to our sketches from functions, essentially. Here, the limit as x approaches 2 from the left. This we called behavior near vertical asymptotes in functions class. And now that we've got this limit notation, we can be succinct in this. And these limits we took in the chapter 1 when we did the chapter on limits, but we're going to use them quite a bit here. So what did we do? Well, essentially what we did is we thought about a little work in the margin here where x is getting close to 2 from the left. From the left means numbers like 1.9 or 1.99, and certainly we thought about, yeah, we could evaluate that numerically, but it's just as easy to think of in our head whether it's positive, each part's positive or negative, because we know it's going to be infinity or negative infinity, right? So this is positive on the top, a normal size positive. It's around 4, in fact. But this bracket, if this is a little bit less than 2, this is going to be a teeny, teeny, teeny little negative, right? Like negative 0.00001 or something like that. This will just be around 6, so it'll be positive. So overall, I've got a positive divided by a negative times a positive. That's a negative, right? That's a big negative. Big negative. So therefore, we'd say the function tends to negative infinity. Right? Dandy. And we would go through the same process here, except for it's on the right side of the vertical asymptote at x equals 2. We'd think of the top still positive, but on this case, this one is also positive, right? Because we're thinking of from the right, this is 2.1 or 2.0000001. Anyway, it's a teeny little positive. And this is a normal size positive. So altogether, we got a positive divided by a positive times a positive. That is going to be a positive, big positive. So therefore, we think f at x goes to positive infinity. And this is the way that we thought about it in functions. And we thought about this in calculus as well, except for we have this limit notation now as well. All right, Danny, and that gives us an idea of the behavior near a vertical asymptote. This one is more like the horizontal asymptote, right? This is as x goes to positive infinity. If I think of the, well, I'll do the quick sketch down here, but now I'm talking about the horizontal asymptote. As x goes way off to the right, well, what happens? Well, we can see the bottom is degree 2, right? It's a quadratic on the bottom and a linear on the top. And when the bottom's bigger than the top, we know the horizontal asymptote is y equals 0. So this is just 0. And I've got a big C note here. So there must be something else going on. And there was. In chapter 1, we talked about there was kind of a more calculus technique to do this. And I want to remind you of that. I'm going to go very quickly through this. So if you need to or want to write stuff down, you can. You don't have to. So this is what we talked about. And this is kind of like the fact we were after using, right? So this is what we wanted to evaluate. And if we wanted to know why this is 0, this is why. I expanded the bottom. And then I factored out x squared so that the bottom here, notice that these are all versions of this. Right? This is going to be 0 when x is really big. This is going to be 0 when x is really big. I can cancel an x out of the top and bottom. I'm left with this 1 over x. You see how I've canceled one of the x's. There's an x left over, and I've kind of split that off. Now, why did I split that off? That's because this value is 0. And as long as this isn't infinity, then I know the whole limit is going to be 0. And this thing over here, by the way I've written it, is not infinity. In fact, this thing in brackets is 2 times 1 over 1 plus 0 plus 0. So this is 0 times 2, which is 0, which is exactly the limit that we expected. But this is kind of a calculus way to show that limit. And when you're asked to evaluate these types of limits to infinity, this is what they want to show. You can know this right away, but you need to show this sort of thing. One little thing that I want to mention here, when x goes to infinity, this thing's positive, right? This thing on the bottom is positive, right? So I've got 2 divided by a positive number. Well, how do I know it's positive? Well, that's 0. And this is pretty close to 0. It's negative, but it's certainly these things are very small compared to 1. So essentially I have 2 divided by 1, right? So this is a positive number. And notice, since x is going to positive infinity, 1 over infinity here, this is a huge, huge positive number. It's going to 0, but it's still positive. So I have a positive number times a positive number, and so I know that the entire thing, the entire function, f at x, is going to 0. Yeah, we knew that in functions class, but I also know that it's going to go to 0 from above. It's going to be a positive number. Right? So that means picture-wise, it's going to look like that shape instead of that shape. And I can get that straight from the limit. How we did this in functions is we would put this idea of the horizontal asymptote together with one of the other properties to know that it goes from above or below. But we were never quite sure. Now, with this kind of fancy way of thinking, a little bit fancy, I can be sure that it's this and not this. Here's another example, just to make sure you've got this idea. For funsies, what happens if we try the limit as x approaches negative infinity of the same function? Well, it's the same process, right? And again, when x is going towards negative infinity, well, this is still going to be 2 over 1, because this is pretty close to 0, and this is pretty close to 0. So this is still 2 divided by 1. This part's still positive. It's around positive 2. But what do I have over here? I've got 1 over a negative number. That means this part's going to be negative. So I have negative times about 2, negative times a positive. It's going to go towards 0, but from below, because it's a negative number. And there's the Desmos graph. I see that. It goes closer to the horizontal asymptote of y equals 0 from below. And on the right side, from above. One of the things we're going to review in today's lesson is our MCV4U function drawing skills. But before that, let's want to go through one more example of this from above and from below business, because it's kind of neat and an important little bit of analysis. So here's a different function. And notice from functions, what we would have thought, we know that this limit is 2 because the degree on the top and bottom are the same, and then I can, just divide the leading coefficients, and it's 2. And how we learned to show that in calculus is using this technique, right? We'd factor out an x, the x's cancel, and then this part goes towards 0, this part goes towards 0, so this whole thing goes towards 2, this whole thing goes towards 1, and when I evaluate the limit, I get 2 divided by 1, which is 2. Okay, fine. But let's think about this a little closer. So, for instance, since it's to subtract this business, it's to subtract a little bit. Almost 0, but a little bit. So this is a little bit less than 2, right? 1.9999, whatever. And this number, because it's 1 plus 3 over a positive infinity number, this is 1 plus a little bit. This is a little bit more than 1. So if I have a number that's a little bit less than 2 divided by a number that's a little bit more than 1, that answer is going to be a little bit less than 2, right? Because 2 over 1 is 2, but if this is a little bit smaller and this is a little bit bigger, it's going to be a little bit less than 2, isn't it? So therefore, this function is going to approach its horizontal asymptote from below. That's that analysis. And there it is, this function. Now, how do we handle this in MCV4U? Certainly we never talked about this sort of analysis in the depth that we did. What we would do, if we wanted to graph this function, we'd draw the horizontal asymptote, but then we'd put other pieces of the puzzle together, like the x and y intercepts, and then we'd say, it must join up. It must join up. But we didn't know for sure because it's possible that it did something like this on us, right? We would never know that in functions class. No idea. But now we can add what we know about the first derivative and see if we've got a maximum or not. By the way, the analysis that we did about the limit to infinity would have shown us that indeed this red thing is the case and not this blue one. But we'll cover that during today's class. I've almost done the entire lesson in the warm-up here. There's the Desmos graph, straightforward. Um, Horizontal asymptote at 2, vertical asymptote at -3. No, nothing weird going on that we wouldn't have been able to know about in functions anyway. This was a boring old rational function. All right, back to the warm-up. We wanted to do that sketch. Do a quick sketch of that graph. Okay, fine. We'd know there's horizontal asymptote at 0, and from the analysis that we did before, this is going to go like this goes like this. Vertical asymptote at 2, vertical asymptote at 4, -4 rather. X-intercept at 0, y-intercept as well. Unfortunately, we don't get anything more there. But let's add these things. We analyze the behavior near the vertical asymptote of 2. So on the left, it goes to -infinity. On the right, it goes to +infinity. I think I can see what's going on there. It looks like this is what's going to happen. Something like that. I don't think it would bounce and go back down, even though I haven't analyzed the behavior near this asymptote, just because there's no other 0 there. There's no other x-intercept. And then something like that. And I think that indeed is what the Desmos graph that we had looked like. Where was it? Yeah, something like that. Something like that. Good. All right. Let's get into the note. Warm up that took what? 12 minutes or something? Yeah, 12-minute warm up. But a lot of the teaching happened there, didn't it? Or review. We'll actually pick up the lesson in part 2.